Hello Victory students, this is Mr. Duncan, and I am making a video about our lesson on trigonometry. And we'll start with the warm-up. It says here, use triangle proportionality and the triangle angle bisector theorem for these warm-up problems. So we look at this first problem. They want us to find x in this figure. Now we see that we have parallel lines here. So that will allow us to say that these segments are proportional to these segments, and actually are proportional to these segments as well. That's by the triangle proportionality theorem. So that means that we can now say that x is to 25 as 4 is to x. So x is to 25 as 4 is to x. That is the triangle proportionality theorem. Cross multiply, we get x squared equals 4 times 25 is 100. Therefore x must be 10. There's our first. So now we know that x is 10. Put that in. And here as well, I suppose. The next thing they want us to figure out is the length of BD. Well, BD is this length right here. We have no information on this side. However, the warm-up does give us a hint. It says, consider using the triangle proportionality theorem. We've done that so far for the first part. And the triangle angle bisector theorem. Well, the triangle angle bisector theorem says if you have an angle bisector in a triangle, which according to this we do, then the sides are proportional to the segment, to the side that's being segmented by that angle bisector. So we can say that DA over AE is equal to DB over BE. That is the triangle angle bisector theorem. So that would mean that 35, there we go, 35 over 10 should be equal to BD over 5. Now hopefully you can see if this is 10 and this is 5, that means this fraction, if we look at it as a fraction, 10 is twice as big as 5, so 35 must be twice as big as BD. So we should be able to figure out BD without doing a whole lot of actual calculations. Just cut 35 in half. That's 17 and a half. But just to test, we should get 10 times BD is equal to 5 times 35 is 150 plus 25, which is 175. And divide both sides by 10, and I get that BD, that is a funky looking B, we'll forgive it, is equal to 175 divided by 10 is 17.5. Just move the decimal line one spot. And that is our length for BD. All right. That being said, it should be noted that this should not say segment BD because it's defined it. We just say, oh, it's right there. This should not have the line over the top of it because the line over the top means we're talking about the object. Without the line over the top, we're talking about the length of that segment. So that is a typo. Next, number 2, it says find the ratios for each of the right triangles. So LM over MN, that would be 8 over 6. And also, folks, we want to simplify. It doesn't say that, but when in doubt, simplify. So 8/6 becomes 4/3. LM over ln over ln. Well, in order to figure that out, this is 6 and this is 8. I know that's going to be 10 because this is a 3, 4, 5 triangle that's been scaled up by a factor of 2. All right, this is 3 times 2. This is 4 times 2. Therefore, this must be 5 times 2. Okay, that's a Pythagorean triple. So LM, we already know is 8. LN is 10. So we simplify that, it becomes 4/5. And lastly, MN over ln would be 6 over 10, which would be 3/5. Okay. On the other triangle, so you'll notice these triangles actually must be similar to each other because they have angle-angle similarity, which means if they're similar, their sides are proportional. So we notice then that if this is a 3, 4, 5 triangle scaled up by a factor of 2, this must also be a 3, 4, 5 triangle that's been scaled up because they are similar triangles. Really key idea here. Well, if this is a 3, 4, 5 triangle, it looks like the orientation is such that it would be 3, 4, 5 to compare to this 3, 4, 5 triangle. Notice the angles give away the corresponding angles and sides. So this should be a 3, a 4, and a 5. So 12 is 4 times a scale factor of 3, and this 5 must be 5 times a scale factor of 3. So that means this side must be 3 times the scale factor of 3, and my pencil just decided that it wanted to run out of lead. Luckily we have a couple more here. Alright, so we have all the numbers, which actually helps us simplify, because when you write out these proportions, you'll notice these are the numbers that'll divide out evenly. So PQ, oh goodness, we're missing that last letter there. I'm guessing that's supposed to be an S. So PQ is 12, QS is 9, which of course is the same as 4 times 3 over 3 times 3, so the 3's are going to cancel out. We're left with 4/3. Interesting. It's the same thing we got here. Okay. So if we look at PQ over PS, that's going to be 12 over 15, and that will simplify if we divide both down to 3 over 5. Excuse me, 4 over 5. My apologies. And last QS, that's 9 over PS, which is 15, and that is 3 over 5. So notice these ratios are the same. They're proportional to each other. So that's the next part. It says, what did you find about the ratios? Well, we find that the ratios are proportional. Now the question is, why is they proportional? We could say this is because the triangles are similar. Hello, Victory students. This is Mr. Duncan, and this is the part of the lesson regarding trig ratios. So it seems some words were cut off here. I'm not exactly sure why I'm being so friendly and saying hello and salutations, but this is obviously supposed to be someplace else. Today we're going to talk about trigonometric ratios. The word trigonometry actually comes from the word trigon, meaning three-sided. Well, a three-sided shape is a triangle. We also can call it a trigon. So trigonometry just refers to the study of triangles. In particular, we're going to be looking at right triangles for this section and the last section. So the big thing we're trying to talk about here is ratios. We are going to talk about specific ratios. So in order to do so, we need an angle of reference. We're going to talk about our reference angle first. So from this reference angle, I now need to name all of my sides. So the side across from the 90 is always the hypotenuse. The side across from the reference angle is called the opposite side, and you need to understand that that is what we will be referring to it from now on. Not the across side, but the opposite side. And this side that is one of the rays that forms the angle, it's called the adjacent side. We will not call it the side next to it or the nearest side. We will call it the adjacent side. That is not pronounced adjacent. It is pronounced adjacent. Okay, so this is the adjacent side, opposite side, and hypotenuse. This is all determined by what angle we make to be our point of reference, or our reference angle. So if I were standing up here, this would still be the hypotenuse. But if this is my angle of reference, this is now my adjacent side, because it is adjacent to that angle, and this would have become my opposite side. So now we want to talk about different ratios we can make based on where our angle is. So on a right triangle, we see that the opposite side over the hypotenuse is one ratio. The adjacent side over the hypotenuse is another ratio. And the only one we haven't done yet would be the opposite side over the adjacent side. That would be a third ratio. Now we could also have any of those ratios written as inverses, and we will talk about those later. But for now, the first one, opposite over hypotenuse. We will call that ratio the sine of an angle. So this is going to be defined as the ratio of the opposite side divided by the length of the hypotenuse. We don't like writing out this long phrase every time to represent this ratio, so we'll oftentimes abbreviate the word sine using these 3 letters. Please be aware, do not pronounce that sin. It sounds incredibly ignorant, and not only is it rude and ignorant to speak that way, but it makes no sense to anybody listening. So this is still pronounced sine, even though it's an abbreviation for this word sine. And to represent it, we would usually say sine of an angle. Well, the angle, we need to give it some reference name, some variable name. So that variable, I'm going to use theta. So we will say sine of theta. Again, this is to denote a ratio, namely of the side across from that angle divided by its hypotenuse. The cosine is going to be the adjacent side over the hypotenuse.
Mr. Duncan, are you missing any tables?
Picking back up. So the cosine of an angle is defined as the adjacent side divided by its hypotenuse. So the length of this side divided by the length of that side. This will be abbreviated using these 3 letters. This is not pronounced cos. Do not say cos. This is ignorant. Say cosine. Even when you see only 3 letters, it's still pronounced cosine. We will say sine of an angle, which is the same as saying sine of theta, or sine theta, or cosine theta. Lastly, the tangent of an angle. The tangent of an angle is going to be defined as the opposite side divided by the adjacent side. And this will be represented again by 3 letters. This is still pronounced tangent. Now the diagrams are very straightforward. We're just trying to draw 3 triangles that represent having these 3 sides in them. So there's 2 ways you can do that usually. Again, we're just going to draw some right triangles here. So if this was my angle of reference, then this would be the opposite side, and this would be the hypotenuse. Without my angle of reference, then this would be the opposite side, and this would be my hypotenuse. And I'm going to draw triangles like this for each of our 3 trig ratios. So for the cosine, this would be adjacent over hypotenuse. Keep it consistent here. So adjacent over hypotenuse. And lastly, tangent, which is opposite, this is my angle of reference, over adjacent. So again, if this is my angle, then this would be opposite, and this would be the adjacent side. Okay, so that's the basic definition of trig ratios. What's their purpose? Well, we get the idea that no matter what size triangle we have, if it's a right triangle and we know the angle here, then it's going to have the same ratio, and it's going to be proportional to any other triangle that has that same angle, because you're going to get angle-angle similarity, just like we saw in the warm-up. So how do you use this to your advantage? Well, we can use trig ratios to solve for triangle lengths. All right, Victory students, we are now going to see the purpose and the use and the functionality of trig ratios. To do so, we're going to show you how to solve for missing side lengths of a triangle. If we know it's a right triangle, we're given one of the sides, and we know one of the other angles. So first of all, you need to identify your angle of reference. In this case, the angle they gave us was 45 degrees. We can use that as our angle of reference. If you prefer, you can change your angle of reference. All we need to do is take this angle, subtract it from 90, and that'll give us the other complementary angle. The only angle that we cannot use is this 90-degree angle, because that angle tells us nothing about the sides of this triangle. All it tells us is that this triangle is a right triangle. But these angles have a direct relationship with how long these sides are. If this angle were to decrease, this side would shrink. So there's a direct relationship between how large the angle is and how large these sides are in reference to it. Whereas this 90 degree does not tell us how big these sides are. So your angle of reference must be something other than this 90 degree angle. So we've chosen the 45. The next thing we need to do is label the sides based on the angle we've chosen. So this is my angle. I can now say that the side opposite it will be this side. Abbreviate that with an OPP. This side here touches that angle. It is the adjacent side. And this side is across from the 90, so this side is always called the hypotenuse. So now we've got all three sides labeled, excuse me. Our next step is we need to see which trig ratio we are going to choose in order to solve for the missing side length we're trying to find. Well, we know we need a trig ratio that has opposite, and the only other side we are aware of is hypotenuse. So we need a trig ratio that has the opposite and the hypotenuse in it. So we look back at our notes and we see that that is the sine ratio. So we can say that sine of 45 degrees, that's equal to the opposite divided by the hypotenuse. So that will be x, that's our opposite side, divided by 16. Now we need to do this, check this first. Sine of 45 degrees, our calculator has pre-programmed into it what ratio is associated with this particular angle when we're looking at the opposite divided by the hypotenuse. So I will go into my calculator, and you'll see I've already typed it in, but I'll do it again. So for me, I put in sine. So we'll put sine, pardon me, sine, there we go, goodness. Honestly, there we are. Sine and then 45 degrees, and I close the parentheses. Make sure I get a decimal number. Now you see this number is peculiar, this 0.85, and the reason being is because if I go into my mode, I'll notice that instead of being in degree mode, my angle is in radian modes. So I need to switch that over to degree modes. If you're using a different type of TI calculator, it will just have an option about 4 sections down and when you go to mode, and it'll either say degree and radian next to it. Make sure you have degree highlighted, and then go ahead and quit out of the screen. So now if I do that same operation again, oh goodness, it seems I have not made the adjustment, so I'll try that again. There we go. So now I get the sine of 45 degrees is equal to 0.7071. We'll round it off. What that means is that we can now solve for a missing variable, because this tells us that for any right triangle with a 45 degree angle, the ratio of the opposite over the hypotenuse will always simplify to this ratio right here, which this is the decimal approximation of. This means we can now figure out what x is by doing some simple algebra. I'm going to cross multiply by the 16. And when I do so, that gives me x on the right side. And 16, I'm going to multiply that now times that ratio. So I'm going to multiply times 16. And I end up with 11.3137 is my answer. So pretty straightforward process. We set up our ratio, and we set it equal to our trig ratio, and then we converted it, and then we solved. Now, when you get better at doing trig ratios and you start to accept that this represents a ratio, you'll no longer need to convert it into this number first. Ultimately, our calculator will do all this converting for us. So I'm going to do the same problem, but instead of converting this immediately into the decimal approximation and then multiplying, I'm going to treat this as a number the way it's written. So the sine of 45 degrees really is this decimal approximation. But just as with square root of 3, I don't have to write it out as 1.71 ... I can just leave it as the square root of 3. Similarly, I can leave the sine of 45 written just like this, and it is understood that that's going to give me a decimal number. So, same problem, sine of 45 degrees is equal to x over 16. Again, I want to solve for x. I'm going to multiply both sides by 16. So I get 16 times the sine of 45 degrees equals x. Under no circumstances should you multiply these numbers together. 45 degrees is not a number that you're going to ever multiply with 16. These numbers are never going to mix. They're never going to add. They're never going to subtract or divide or multiply or square or anything else. This tells me that I'm looking at a ratio associated with the 45 degree angle. This says I'm going to multiply this ratio by 16. So that is exactly what I'm going to do. I'm going to type in 16 times the sine of 45 degrees. And you'll notice I get the same answer out I did before, because the sine of 45 degrees is that ratio. So I will write that out just so we have both things to look at. And I'll say, hey, look, they are the same. So this saves me from having to do the conversion and then solving using algebra. I can just treat this as a placeholder for this ratio. All right, so let's go ahead and turn the page. In this first example, it asks you to find the different trigonometric ratio for each of these quantities. I highly recommend you try and do this without my help first, and then go ahead and look forward at the video. So if I were you, I would pause at this point, try this for yourself, and then continue on. Okay, so I need to find the sine of angle S. Well, I see that this is a 30-degree angle in a right triangle, meaning this other angle must be 60 degrees. This is a special right triangle. That means I already know what the ratios of these sides are using special right triangles. This will be 2x. This is across from the 30, so this will be the x, and the across from the 60 is x square root of 3. So these are the proportions for the sides of a special right triangle. So these, finding the sine of angle S should be pretty simple. For me, I can simply set up the ratios already. So this is 17. This side should be half the length of the hypotenuse, so this will be 8.5. And this side should be the square root of 3 times bigger than whatever this number is. So it's going to be 8.5 times the square root of 3. So the sine of angle S, if this is my angle, then this would be my opposite side, and this would be my hypotenuse. It's across from the 90 degree. So sine would be represented by 8.5 divided by 17, which of course will simplify to 1 over 2. And if you type in sine of 30, so we'll try that, the sine, oops, of 30 degrees, oh goodness, there we are. We should get, again, the same ratio. Sine of 30 degrees is 1/2. And indeed, that's what we're doing. We're taking the sine of angle S, which is the sine of this angle, which gives us 1/2. And it will always give us 1/2. Why is that the case? Well, because no matter what the side lengths are, I know what the proportions are going to be. The sine of 30 degrees, no matter if it's this triangle or any other triangle, if it's a right triangle and that's 30 degrees, the sine of 30 degrees will be defined as this length divided by that length. Well, this length is of the proportion x compared to 2x. So however long this side is, this side's always twice as big. This will simplify. If you notice, they have x in the denominator and the numerator. They divide out, become 1. This simplifies to 1/2. So no matter what, the sine of 30 degrees for every single triangle, no matter how big or small, if it's a 30-degree angle in a right triangle, the sine of it's going to be 1/2. It's going to be a ratio of 1 to 2, which we already knew that was the case. All right, we'll move faster now. The cosine of angle S, that would be the adjacent for this angle, the adjacent over the hypotenuse. So that's 8.5 square root of 3 over 17. And that simplifies to the square root of 3 over 2. And we can check that, of course. So if I type in square root of 3 divided by 2, I get 0.866025. And if we do the same thing now, but with the cosine of 30 degrees, we also get the same ratio. Now, interestingly enough, my calculator will actually give me the exact form if I leave the decimal off. And as you see, the cosine of 30 is the square root of 3 over 2, the exact same ratio we received. Okay, last one, tangent of angle S will be, for this angle, opposite over adjacent. So that would be 8.5 divided by 8.5 times the square root of 3. Well, the 8.5's divide out. We get 1 over the square root of 3. And we don't like having denominators of square roots, so I'm going to multiply top and bottom by the square root of 3. That'll rationalize this denominator, because the square root of 3 times the square root of 3 is 3. Because it'll give you the square root of 9, which of course simplifies to 3. And the top is now 1 times the square root of 3, which is just the square root of 3. So this should be the tangent of 30 degrees. And again, we can check that. Tangent 30 degrees is indeed square root of 3 over 3. With that said, I don't believe you need me to go over these as well, because ultimately it's going to be repetitious. What you will notice is that the sine of this angle is going to be the cosine of the other angle. And that should make sense, because if we look, the cosine of angle P will be 8.5, that's the adjacent side to angle P, divided by 17. Well, that's exactly the same numbers we were using here, because now we're standing in a different position, so it makes sense that now we're going to see those same ratios show up, just maybe in a different order. The only real difference will be the tangent of angle P. Instead of it being the same ratio as ours, it's going to be inverted, because the tangent of angle S would be 8.5 over 8.5 root 3, whereas the tangent of angle P would be 8.5 over 3 over 8.5. So those are going to be inverse operations to each other. Okay, so moving on, the next thing that I ask you to do is to calculate these trig ratios. To do so, you just substitute, or just type into your calculator tangent of 40, sine of 78, and so on, and generate your decimal approximations. This is just for you to become comfortable with the fact that these really are just ratios, guys. This is a placeholder for a ratio for us. So I'll do the first one. Let's see here, tangent 40 degrees. And I end up with 0.8391, so 0.8391. And you go to the next one, same way. And you get a longer one this time, so this is 0.978. And let's go out to the next decimal place, so that's 9781. The 4 does not round up, so it rounds down. Almost does, doesn't it? Okay, so you can continue on this way without me, so that is an exercise I will leave to you. We're now ready for example 3. So this is where we actually start solving for right triangles using the information we now have about us. Okay, so we're asked to find x and y, the lengths of those. We know this angle is 35 degrees. So here's our angle of reference for convenience. We could use this angle. It would be, what, 55 degrees? We could, and we could solve it if we wished. But I'm going to use the one that they've already given us. It's just as convenient. Let's see here. So from our angle here, this is the 90, so this is already the hypotenuse. That's always true no matter which angle we're using as our reference, either one of these. If this is my angle, that's the hypotenuse. The other side that touches this angle is, of course, the adjacent, and the angle directly across, or sorry, the side directly across is the opposite. Okay, so those are my labels. Okay, so we need to decide, do we need to solve for x first or y first? And it appears that they are equally matched. So I'm going to solve for y first, because I wanted you to see that it's a little bit different this time for us. It's going to have a slightly different setup in terms of solving. So if I want to solve for y, that's the hypotenuse. The only side length we have to work with is this adjacent side, so I need something that has both adjacent and hypotenuse. At this point, if I haven't said it yet, I will say it now. There's an easy way to keep track of all of your trigonometric ratios. It is a phrase we've been using for at least a century, probably more, and it looks like this. So written out as one phrase, it would be so ka toa. SOHCAHTOA. This phrase SOHCAHTOA is a mnemonic device to help us remember which trigonometric ratio is assigned to each of its names. The names. So sine is associated with opposite over hypotenuse, cosine is associated with adjacent over hypotenuse, and tangent is associated with opposite over adjacent. So we look back to what we needed. We needed, in order to solve for y, the hypotenuse and the adjacent side. The only one that has hypotenuse and adjacent is cosine. So we will say that we need cosine of 35 degrees, and then we will say that is equal to adjacent over hypotenuse. And in case you can remember the order, that's the way these are stacked, so they are actually written in fractional form. So adjacent goes on top, so that's 11.2, and the hypotenuse is y. Now, we want to solve for y. We can't just multiply both sides by 11.2. Some of you are trying to do so and you're failing miserably to get the answer correct. And that is because, think of algebraically what we need. We want y to be by itself, and we want it to be in the numerator. We want y equals something. So to get it out of the denominator, I'm going to multiply both sides by y. When you do so, you get y times the cosine of 35 degrees equals, well, those cancel out, 11.2. Excellent. So now y is out of the denominator. To get it by itself, we're going to isolate it by dividing both sides by the cosine of 35 degrees. You will never divide just by 35. Okay, this is not a number the way 11.2 is a number. It is not. Please do not treat it as such. This is an angle, and this is a ratio that's associated with that angle. So guys, this is a package deal. They stay together. That will give us y equals 11.2 divided by the cosine of 35 degrees. So now this is definitely a calculator problem. So here we go, 11.2 divided by the cosine of 35 degrees. And I get 13.6727. So that's a decent way, decent enough. So now we have solved for y. Some of you may recall that this is the type of problem that I would totally be using my slide rule for. So just to remind you how that looks, same problem. Slide rule says I can slide this y up into the numerator, I can slide this guy down into the denominator. If I do so, I end up with y over 1 equals 11.2 over the cosine of 35 degrees. I just slid this guy down, this guy up. And notice, it's the same exact setup that you have here, right? Y is equal to 11.2 over cosine 35, same thing here. So you're going to get the same answer. So I'll point and say, hey, it's right there. Same answer. Okay, so we need to solve for x, and ultimately, since you now know what y is, you now have two sides of a right triangle, so you could use the Pythagorean theorem to solve for x. I would caution against it. The reason being is this number has been rounded off. It is an approximation, meaning if we do use it for our calculations, there's going to be some error that has creeped in there. Instead, I'm going to use the numbers they've given us because those are exact as far as we know, and I'm going to use trig ratios again. So now I want to solve for x. That's the opposite side of this angle. And again, the only side that we have exact value for is the adjacent. So opposite over adjacent, those are the two ratios I need, or the two sides I need to make a ratio. So I look, the only one that has opposite and adjacent is tangent. So we will say the tangent of 35 degrees equals x over 11.2. So this is the easier type of problem. The only thing I need to do to get x by itself is multiply both sides by 11.2. If I do so, I end up with 11.2 times the tangent of 35 degrees equals x. So this is an incredibly fast problem. So 11.2 times the tangent of 35 degrees. And that gives me that x is equal to 7.84232. If you don't believe that these numbers are correct, you can check them. If you square this number, square that number, add them together, you should get this number squared. That's the Pythagorean theorem, and that's an excellent way to verify that the work you've done so far is correct. All right, last piece. Turn the page over. We have an application problem. I highly recommend you do this application problem before I dive in. I will make one note. I don't know why, but I put the question mark here, but really the distance we're trying to find in this picture is right here. So this I will call x for our unknown length. So if you pause the video, try knocking out this problem without me. Okay, here we go. So it says, how far away is Florida Cuba from the intersection of I-10 and Highway 6? So we want to know how far away is Florida Cuba. You can see it written right here. How far is that away from this intersection? Well, this obviously is the right triangle we're dealing with here. That's the point of this problem. We see that we know this length, we know this angle, and we want to know that side. So this angle, that's the side opposite it. So that will be OPP. This will be adjacent. So we will use a trig ratio that has opposite and adjacent. So if I quickly write down SOHCAHTOA, the only one that has opposite and adjacent in it is tangent. So I will say that the tangent of 39 degrees is equal to x, that's the opposite side, divided by the adjacent side, which is 5.3. So that's our equation. We're now going to multiply both sides by 5.3. That gets the x by itself here. So we get 5.3 times the tangent of 39 degrees is equal to x. And so now we are ready to substitute our numbers in and calculate. Oops. Syntax. Come on. There we go. So I get 4.292 miles. I should say approximately, because when we're dealing with trig ratios, we're having to constantly round our numbers off. So that's our answer. Good to go. Well, we've now learned that you can use trig ratios to find missing sides of right triangles. And guys, that's the thing you have to keep thinking. Trig ratios help us find missing sides of right triangles. It says, hey, you give me an angle, and I'll give you a ratio assigned or associated to that angle. So if I worked backwards, what would the opposite of that be? Well, the opposite would be, if you know a ratio, then can you give me the angle that's associated with that ratio? And the answer is yes. We call these inverse trig ratios. And so that's what we'll be doing in A, B, and C here, and that'll be us for the day. Oh, interesting. They both have 2 example 4s. Typo. So that should be example 5 now. All right, so we're trying to find the measure of an angle. Specifically, let's try to find the measure of angle x. So this is going to follow the same 4 steps we've used already. The only difference is now we're going to be using an inverse trigonometric ratio. And the way you can see those is next to each one of your trig ratios. You'll notice in a different color is that same trig ratio, but with a -1 superscripted. That does not mean raised to the -1 power. This is a notation that we use in set theory. And in truth, a couple of the other math teachers, we've talked, and we want you to make sure you're aware that this notation is not always used elsewhere. If you're using the computer to do your calculations, sign of -1 doesn't make sense to the calculator all the time, so you may have to write it in a different way. So we will make sure you're aware of that as we do this problem. So again, let's proceed. We want to solve for this angle. This side would be the opposite side to that angle, and this would be the hypotenuse. So in order to figure out this angle, I need a trig ratio that has opposite over hypotenuse. Well, that is, of course, the sine. We can see that from SOHCAHTOA. So opposite over hypotenuse. So we're going to use the inverse sine in order to find the measure of angle x. So we're going to use sine inverse of our ratio. Well, the ratio, of course, is opposite over hypotenuse still, so that'll be 10 over 14. You don't need to simplify, you can leave it just like that. And now this is very much a calculator problem. So I'm now going to use that other function, so now I have a sine inverse of 10 divided by 14. Now when I type this in, it should give us an angle, and it does. It gives us 45.5847 degrees. Do we need to go that far out? Not really, but that's okay. We have now. Now, I want to see if we can do the same thing to find the other angle. And here's the thing, guys. We already know what the other angle is going to be. If that's 90, we've just figured out this angle is 45.5847. And this angle should be the complement to this angle, meaning they should add up to 90 degrees. So if I subtract 45 let's just go to 58. Make it a little bit easier on poor Mr. Duncan. This becomes 44.42 degrees. So we found the measure of angle Z, but let's confirm that using inverse trig ratios just to show proof of concept. So the measure of angle Z, is equal to, and now for angle Z, our sides now take on slight change. From the point of view of angle Z, this is not the opposite side, this is its adjacent side, but that's still the hypotenuse. So we need a trig ratio that has adjacent over hypotenuse, and we can see that would be the cosine. So we'll use cosine inverse because we're trying to find an angle. And now the ratio is still the same, 10 over 14, but we're referring to it from the point of view of a cosine, not the sine. So we take the cosine inverse of 10 over 14. Let's see what we get. So cosine, inverse of 10 divided by 14. And sure enough, we get 44.4153. And if you round accordingly, that 5 would round up. This would become 44.42, which is exactly what we predicted it would be. So these things are well met. And you can see that those two angles, if you add them, do add up to 90 degrees as well. All right, that is the end of this lesson. The other two problems here I will leave as practice for you, both of which follow the same exact practice of choosing an angle, labeling your sides, determining which trig ratio you're going to use, and in this case the inverse trig ratio you're going to use, and then writing that inverse trig ratio, and then putting inside of it the ratio of the sides, and then using your calculator to do a calculation from there. The only last note I need to make with you is, what's the other name for sine inverse? Well, sine inverse of a ratio. I better put a ratio here. Let's put x over z. Sure. Just numbers now. That is equivalent to saying arc sine. Cosine inverse is the same as arc cosine or arc cosine, and tangent inverse is equal to or equivalent to saying arc tangent. Okay, so all of these, if you see this, it means the same thing. These are equivalent, folks. So please be aware of that all of these mean the same thing. So sine inverse, arc sine means the same thing. It performs the same function. This term, I think, is more useful, and you'll see that when we start talking more about circles and how circles come into play in figuring out these ratios and their connection there. That's all for now. Hello, Victory students. This is Mr. Duncan, and this is the part of the lesson regarding trig ratios. So it seems some words were cut off here. I'm not exactly sure why I'm being so friendly and saying hello and salutations, but this is obviously supposed to be someplace else. Today we're going to talk about trigonometric ratios. The word trigonometry actually comes from the word trigon, meaning three-sided. Well, a three-sided shape is a triangle. We also can call it a trigon. So trigonometry just refers to the study of triangles. In particular, we're going to be looking at right triangles for this section and the last section. So the big thing we're trying to talk about here is ratios. We are going to talk about specific ratios. So in order to do so, we need an angle of reference. We're going to talk about our reference angle first. So from this reference angle, I now need to name all of my sides. So the side across from the 90 is always the hypotenuse. The side across from the reference angle is called the opposite side, and you need to understand that that is what we will be referring to it from now on. Not the across side, but the opposite side. And this side that is one of the rays that forms the angle, it's called the adjacent side. We will not call it the side next to it or the nearest side. We will call it the adjacent side. That is not pronounced adjacent. It is pronounced adjacent. Okay, so this is the adjacent side, opposite side, and hypotenuse. This is all determined by what angle we make to be our point of reference, or our reference angle. So if I were standing up here, this would still be the hypotenuse. But if this is my angle of reference, this is now my adjacent side, because it is adjacent to that angle, and this would have become my opposite side. So now we want to talk about different ratios we can make based on where our angle is. So on a right triangle, we see that the opposite side over the hypotenuse is one ratio. The adjacent side over the hypotenuse is another ratio. And the only one we haven't done yet would be the opposite side over the adjacent side, though it would be a third ratio. Now, we could also have any of those ratios written as inverses, and we will talk about those later. But for now, the first one, opposite over hypotenuse. We will call that ratio the sine of an angle. So this is going to be defined as the ratio of the opposite side divided by the length of the hypotenuse. We don't like writing out this long phrase every time to represent this ratio, so we'll oftentimes abbreviate the word sine using these three letters. Please be aware, do not pronounce that sin. It sounds incredibly ignorant, and not only is it rude and ignorant to speak that way, but it makes no sense to anybody listening. So this is still pronounced sine, even though it's an abbreviation for this word sine. And to represent it, we would usually say sine of an angle. Well, the angle, we need to give it some reference name, some variable name. So that variable, I'm going to use theta. So we will say sine of theta. Again, this is to denote a ratio, namely of the side across from that angle divided by its hypotenuse. The cosine is going to be the adjacent side over the hypotenuse.
Mr. Duncan, are you missing any tables?